Let's see. So we are joined this morning by Dr. Yair Goldberg, who is a faculty member at the Faculty of Industrial Engineering and Management in the Technion Israel Institute of Technology, where he's also the Vice Dean for Graduate Studies. Prior to his current position, he obtained his PhD in statistics from Hebrew University and carried out postdoctoral research at North Carolina, Chapel Hill. And his research interests lie at applying statistical theory and machine learning to address both theoretical questions and real-world problems, with a focus on developing machine learning tools for handling missing data, uncertainty estimation, and also higher dimensional problems. And we're really lucky to have him here today to talk about the work he's been doing on COVID-19, as he's part of the research team that advises the Israeli Ministry of Health for their COVID-19 response. So I'll let him take it away. I'm really excited to have him.
First of all, thank you very much for the invitation. I share my screen. Okay, so this is a really great opportunity to present our study. I'll start in the beginning with just explaining a little bit how did this study came out and how we started with that. This is a study that took about 5 days, and later on we made it much bigger and much more thorough. But in the beginning, we started I had to give an answer to the government in really 5 days. They wanted a report, and that's what you're going to see here. So as Spencer said, I'm a biostatistician at the Technion, and I joined the team at the beginning of the pandemic in Israel, the Israeli Epidemiologist Center, which is what's called here the Gertner Center Institute. Okay, the Gertner Institute was asked to help, and this is a very small center, and they really just asked many people to join. And we had a team of about 50 people, and you see 9 of them here on this slide. So we had, these people came from very different disciplines and very different backgrounds. And here you see Chagai Katriel from Goldberg, which is one of the colleges in Israel, Amit Huppert and Rami Yair. Rami is my first cousin, by chance, we just got to work together. And all of them are modelists of pandemics. Nona is our data scientist. Itai is a good friend from University of Haifa, also a biostatistician. And here you see Nurit, Yoram, and Yoav, who are all officers in the army who joined us, are all operation research guys. And some of them are very highly ranked. So Nurit is a colonel, and Yoram is, as I checked, and it's a brigadier general. I don't know, very, very high ranked, and almost. So that's the team. We got to work together. We worked on many, many different problems. Some of them for 1 day or 2 days. We were asked to advise the government if there is a second wave, how many ventilation machines to buy, how many people are sick now, how many people are going to be sick in a week. Some stuff really, in a day you had to give an answer, some in a week. And at the end of the first wave, after a very, very strict lockdown, we were asked to give a report about opening schools. And somehow we got a great data, and in 5 days we got some solution, and I'm going to discuss that with you. And later on, we had some more data, and we got even better results. So that's the work I'm going to share with you. And at a year from now, a year ago, the question was, do children infect at all? And as you can see here from The Guardian, a boy with COVID-19 did not transmit disease to more than 170 contacts, which is, as we say in mathematics, that's a proof by example. But it wasn't clear if children infect. We already had some data on that. We knew that children do infect. As you can see here, this is 3 families from our data, and the days from symptom onset. And you can see families with only kids that are infected, and the family is in quarantine. And you see the first kid, the symptoms are on day 0, the second kid on day 6, and the third kid on day 15, which really indicates that kids do infect each other, and you can see other families, and we have more of that. So we knew that children infect, but we didn't know how much, and that's the goal of this research. Okay, so although I have 5 parts, each part is about 2 slides, and I'll try to stay in the 20 minutes I got. So a really short introduction, then I'll explain something about, I'll tell you something about the city of Bnei Brak, which is really unique. Then talk about the data we had. We had really great data, the model we developed, and the results. Okay, so as I said, clinical characteristics of disease among children are different from those of adults. And the questions are children less infected than adults? Are there less infectious than adults? And do they have milder symptoms? And I think we all know by now that the answer to all of these questions are yes. Children are less infected, they are less infectious, and have milder symptoms in general. But back then it wasn't that clear. And one of the questions is related to the fact that children are tested less. And that's a fact. These children are tested way less than adults. This could happen because they are less infected, but also because they show fewer symptoms. So that's the other option. And there are other reasons that related to the fact that if the children are at home, some parents don't take them to test because anyways they are in quarantine. So that's the question. I'm going to discuss 2 main terms: susceptibility, which is susceptibility of children relative to that of adults, because we always compare to something, and we are going to compare susceptibility of children to adults, and this is how much children get infected. And then infectivity, which is how much children infect other people. As I said, we are going to use a unique data set from the city of Bnei Brak. And this data set is very unique because of 2 things. First of all, all household members were tested. And this is important because of the detection bias that we usually have in other analysis, because most children are less tested. So here we have families that everyone was tested, and so we can get better conclusion or less biased conclusions. The second reason that this data set is very unique is because the households are large, and this helps us to actually understand the dynamic within the household. So assume a household, all the people in the household are already in quarantine because say the index case got into the household and he or she is already sick, and all the other people get into self-quarantine. Then what happened in the family is sort of, I would say, a pandemic within a household. And when the household is large, we can learn something from that structure. And so that's how we did our analysis. Okay, city of Bnei Brak. As you can see, that's a picture, and this no high-riser, very, I would say, open city, very close to Tel Aviv. As you can see here, very small one. This is Tel Aviv, this is the beach, this is Bnei Brak. This is, as I said, very small city, 7.1 square kilometers or whatever in miles, and about 200,000 residents, which is not large for a city in Israel. But look at the fertility rate, which is about 6 children per woman. This is even to Israel, which we have a lot of kids, 2.6, 6 kids per woman on average. This is really, really large. Not the largest in Israel, not the highest in Israel. The highest is about 7 in one of the ultra-Orthodox communities, but this is one of the largest. And it's really not unusual to see families with more than 10 children. My father has a cousin with 18 kids in Nepal. Finally, this is one of the poorest and densely populated cities in Israel, and actually even in the world, as you can see here. This is from the wiki. Bnei Brak is the 10th populated city in the world. And the dynamic of the pandemic in Israel was very different from that of Bnei Brak because the city is so dense and because people do not listen to regulations, do not obey regulation very much. It's a very ultra Orthodox city. And so the entire city of Bnei Brak was placed under an army-enforced lockdown due to the coronavirus outbreak. It was so really different from all other places in Israel. Much higher. I'll show you graph in a second. So that's the data, that's the city. And now I'll talk about the data. So the data we have is on 637 households and about 3,000 people. So think about it. All members were tested for COVID-19 using PCR. And later on, this I'm not going to show you, but if you look at the paper later on, we had the chance to actually do a serological testing for about 1/4 of the families. And that really helped us to get better results. As you can see here, this is the dynamic in Israel during the first wave. And this is the dynamic in Israel during the second wave. This is like April, and this is about, as you can see, July. And this is what happened in Bnei Brak. So really different. And this is the time of our research, starting, roughly speaking, the beginning of the first wave and the first lockdown of Israel that took 6 weeks. And it finished at the end of the lockdown, and you can see a very good going down, the curve going down very nicely. Okay. So a little bit more about the data. So we had, as I said, about 630 families. Some of them are small, but as you can see, we have large families. Some of them have more than 10 household members. As you can see, about 50 families with more than 10 household members. Another interesting thing is to see how many positive people are in these families, these households. So as you can see here, for example, families with two members, usually mostly adults, 2 adults. So there is the index case that is always has to be positive, and then there is the second adult or second member. So as you can see, about half of them got infected, and about half of them did not get infected. That from the adults in that share the same household. If we are looking at families with 8 members, what you can see here, it's not exactly uniform, but you don't see much going down at a family when positive number are 5, 6, or 7. And this is interesting because this indicates that there are inside the household infections. And that's exactly the model we are trying to use here to take into account the fact that there are infections within the household. Okay, another interesting fact is the number of the positive fraction per age of PCR, and this is excluding the index case because the index case is for sure positive. And as you can see here, this is going linearly up, and then this is a roughly same plateau. Okay, and this says that even that indeed children are less positive, as you can see here. And they get, all of them were tested, but the percentage of those who were positive PCR is lower, is less as they're going down in age. If we focus on the ages between 1 and 20, we see roughly the same result, with one exception, which is between 0 and 1. If we want to guess why, you're almost welcome. Any suggestions? So it's interesting. We actually don't know why this happens, but we suspect that 2 main reasons. One of them that children between the age of that are less than 1 year old are breastfed, and they are very close to the mom. And then if the adult is infected or they are held by the adult, they have more chance to get infected. That's one reason. The second is that their immune system is less strong, and that may be another reason for that. Okay, that's about the data.
One thing on that, actually a question. So we've actually seen a similar trend looking at hospital admission numbers, we see a kind of sharp decline in ages until there's like a small spike in the 0 to 1 age group. And I wonder if, so we've hypothesized that maybe with newborns, like parents are more careful with them and kind of will try and get them tested more regularly, or bring them into the hospital if there's kind of any symptoms, versus maybe waiting a little bit longer for children. I wonder what you think of something like that.
That's definitely could be, but here again, just because everyone was tested, so the fact that we see a different positive fraction make me suspect that this is related to a different reason. But you are right, that's definitely for hospitalization. I would assume that your suggestion is it makes a lot of sense. But because it was tested, the fact that they have different positive fraction means that they are probably more infected actually.
Were you able to look at cases where the mother was infected versus where the mother was not infected?
Well, that's a good question. I was asked that, and I have to say, we actually have the data for that. And when we did the research, we had no time at all. And later on, that question, we had different questions to answer. So in the end, I'll tell you what we are doing now. But we never went back to that. So I started to work on that and stopped because we have really individual level data. So we could know that. But good question. Maybe I should try to look at it again. Now we have even way more data, actually. But again, we didn't go back to that question since then.
And
okay.
Darlene has a question: how frequently were household contacts tested once an index case was found? Okay,
very good question. I have a slide on that, but because of the time limitation, I deleted a few of those slides. So it depends. It's really, again, at the beginning of the pandemic. And so we know that most people were not infected previously, which we don't know now anymore. But because of that was the beginning and testing was expensive and not a lot of testing was done. So some of the families, all the family members were tested many times. Some families less than that. I really have, if you can go to my, you can actually see, we have a graph for every family in these families, and you can just see exactly how it looks. We uploaded all the data we have. So you can see a family by family, how many were tested and when exactly. So some more, some less, and it's really varying. Right. Okay. So let's talk about the model. So again, as I said, we are interested in two parameters, relative susceptibility, and we define relative susceptibility and relative infectivity. Those are the two parameters we are interested in. So we define relative susceptibility of two individuals as the ratio between their probabilities of being infected per a unit time when they're exposed to the same infection factor. So roughly speaking, if we have here an infectious someone, and we want to check how much a child is susceptible to get infected, or an adult, assuming everything else is the same, and we denote that by probabilities that infections will infect a child or an adult. We are talking about the ratio between these probabilities, which we denote by gamma. So gamma is the relative susceptibility. How much a child, I would say less infected, less infectious, less susceptible, than an adult. We will denote it by gamma. Similarly, we are talking about how much a child is infectious compared to an adult. And again, I'm using the notation, but here the child is first. Probability is that the child will infect the infected, or the adult will infect the infected. And assuming everything else is the same, and I'll denote that by delta. Okay, so that's the two parameters that I'm interested in. And I'll say in advance, roughly half both of them. So that's the results we got. And it will be easier for us to think about half. So let's look at this table. So adult to adult, let's say that the probability that adult will infect adult, say during a week or during the pandemic in the family is PAA, P adult adult. We would like to talk about the probability that adult will infect a child. Again, because child is less susceptible, we expect it to be less. So we'll define the probability that adult will infect a child to be gamma, that's the susceptibility ratio, multiplied the probability of adult to adult, say half that of that adult. And similarly for a child, since child is less infectious, we expect the probability that a child will infect an adult to be delta times the adult to adult, probability adult to adult, or say half, rough. And when we are talking the probability that a child will infect child, the child is less infectious. And this child is less susceptible. And we expect the child to be, the infection of child to a child to be gamma delta multiplied by PAA. So let's say quarter, if we believe that gamma and delta are half, the probability that the child will infect a child is quarter that. It's 1/4 the probability that the adult will infect an adult. So that's, roughly speaking, the three parameters we are going to estimate in the model. Another thing I need before I present the model is the generation time distribution. And generation time is defined as the time, the probability of infection, given that the time lag between infection in the primary case and the secondary. So think about someone who just got infected. There is, and the probability that you infect is divided over the days. So the first day is less infectious, the second more, third more, and after 14 days, we believe they don't infect anymore. So this generation time distribution, I have to say, it's very hard to estimate, and we spent a lot of time to estimate it, because for actually estimating this data, you need someone to get infected, to know when was the index case infected, and when was the secondary case was infected. And we used epidemiological investigations from Israel. At the beginning, there were a lot of those, and we had like very detailed, and some people you knew exactly when they got infected and when they infected other people. So we had some estimation, and Rami, who was responsible to that, changed this distribution every day, I think to annoy me mostly, because I had to change all the calculation based on that. But it was not big changes. Again, anyway, he's in family, so I can't complain. So the model dynamic. So assume that at day 0, we have a family with one adult who is infected, the index case, and one adult and 4 children that are susceptible. And we want to look as time goes what's going on in this family. So assume at day t-1, a child was already infected 2 days ago, and now we have 1 adult and 3 children who are susceptible. And we'd like to know what's going to happen, what's the probability that tomorrow we'll have another adult who is infected or another child who is infected. What do you see? What do you think? So this is roughly speaking, this probability that a new adult will be infected depends on the probability that this adult will infect him or her, or that the child will infect the adult. Okay, and this depends on 2 things: the probability that adult will infect adult, and on the generation time, because if t is 14, probably this probability is 0. If t is 5, then there is much more chance that the adult will infect the adult. So the probability is given by the following formula: probability that adult will infect an adult multiplied by the generation time of t days, plus the probability that a child will infect the adult multiplied by the generation time, based on the generated time of 3 days. So that's the formula. What about children? Really the same, just replacing the adult here and the adult here with a child. So that's the model, and I'll be a little bit more rigorous and really just a little bit. I have more slides, but I put only 1 more, and this is the one. So this is roughly speaking an SIR model within a household. So we have the susceptible, we have those who become infected. It's the same process the susceptible process and the infected process. We just don't have the recovered because it's a short pandemic within the household. The probability that adult will be infected on day T depends on how many infected adults were infected tau days ago and how many children infected were tau days ago, multiplied by the relative probabilities, the respective probabilities, and the generation time. And the dynamic works like that. The number of infected on day T from the adult group is binomial with the number of susceptible, that's the N. And the probability here is not exactly PA, it's 1 minus e to the minus of PA. But when PA is small, think about 1 minus e to the minus x is roughly x. So we see here roughly the same. This is the same for children. So infection process is binomial given the susceptibles. And this update of the susceptible is the number of susceptible the day before minus those who were infected. And again, if I'm sure you're familiar with the SAR, this is roughly speaking an SAR within a family. So now we want to estimate our parameters. Oh, I'm talking too much. What time is it now? Okay, I'll try to be not too much. So say that at the end of the pandemic within the family, there is one adult and 3 children that are infected, and one adult and one child that are still susceptible. So in that case, we would like to see which of the parameter values of PAA, gamma, and delta are likely to generate such a family. And Tn different between different families. Analytic solution is very difficult. And what we did, we just, for each set of parameter values, we actually simulated possible families that go through this dynamic I just described and try to see which is the most likely to happen. And we did it over all the data that we have, 330 families. And we created a dictionary of distribution for the dynamics. So for each adult and number of adults, for each family type, number of adults, number of children, index and duration. And for each fine grid of the parameters, we got more than, I don't know, many rows. It took forever I used many of these servers that I asked my friends in the Technion to let me use. And we did it on them. And we calculated the likelihood. And I really spare you so many difficulties that we had to do that. But once you have this dictionary and you know the index case, you can do it very fast. And we calculated the MLE using this data. And we also used, we calculated confidence intervals using parametric bootstrap. Okay, so that's roughly speaking what we did. And I'll show you the results. So this is a likelihood surface. And as you can see here, this is the susceptibility axis. And if you can see here, the likelihood surface is very narrow because we had a good estimation here. The infectivity is less good. It's much wider. Just the reason is that most of the index cases are adults. So to estimate susceptibility of children, it was easy to use all the data. To estimate the infectivity, we actually used mostly the second infection, the second wave of infection within the family to estimate that. And that's difficult, and we had less data. So these results are not as tight. We used the confidence interval, as you can see here again. We had good estimation of the parameter PAA and gamma, and a wider confidence interval for delta. The final results that we got, you see here, are based on more data that we got later. That's not exactly because what you saw in the previous slides, we got, as I said, a lot of serological data later on, and it helped us to make our model much more precise. And our final estimates are about half the children are less susceptible. Gamma is about half, let's say. And children are less infective than adults, also about 0.63. And children do exhibit symptoms. A little bit of future research. So we did a lot of work on nursing homes. The schools were much more difficult to get data in Israel because of privacy issues. Although we really asked and did a lot of work to get data from school, we didn't get much. We got a lot of data from nursing homes, but still it's very difficult to analyze the data because of the different, like I would say, small pandemics which in nursing home. We would like to understand better the biological mechanisms that make children less susceptible and less infective. I'm sure that now there are more results, and I admit I don't follow anymore this literature, so I don't know what's going on. One thing that was suspected back then, at least, was that common cold, which is also SARS something, gives some immunity to children. But I don't know if this is correct. This may be related to what I showed before. Finally, we are actually working about handling missing data because we have, we all have a lot of serological testing from many families, but this is usually not full, and we try to solve that too. Okay, so thank you for your attention. If you have any questions, and I'll just take one more minute of your time just to tell you what we are doing now, because I'm very excited about that. So we are checking how long is the protectiveness of both vaccinations and of previous infection against reinfection or other outcomes like hospitalization. So we have people who infected a year ago and not a lot of reinfections, especially in Israel. We know we have the numbers and they are not very high. And the question is, how long is the protection that you gain because you were previously infected or because you got the vaccination? Okay, so thank you very much. I'll stop here.
I'm curious,